Hey, let's talk a little bit about shaders. So shaders are little programs that can run on your GPU, your graphics processing unit. And today, GPUs are very powerful. We have GPUs that are in common usage that have hundreds or even thousands of cores, which are like essentially little processors all packed together. And so with these processing cores, a GPU can split up all the work that needs to be done in order to put pixels on the screen. All that work can be done across all these different cores, these processors, and then the result can be shown on the screen really easily. So extremely powerful, and we want to be able to harness this power. As programmers, we can write code that runs on each of those little cores, and that code is shader code. So in Unity provides a structure for us. So we can create shaders in Unity, we can apply them to surfaces and give them, make creative effects on them, or use them to calculate like realistic lighting effects and such. When we look at a shader in Unity, we're going to see that it's a little different from shaders elsewhere, but there's fair reason. So let me see, where is a good place? Let me make a new folder, shaders, and let me create a shader. So if you right click, you go to create shader. There are several options here. Standard surface shader is going to involve lighting information, and so you have to use mathematics to determine how the light is bouncing off of a surface and whether it's like shining right, bouncing and shining right at the camera, or if it's just giving a diffuse effect on it. So those are somewhat complex, but there are a lot of built-in Unity functions to make it simpler. There are unlit shaders, which is what I'm going to use right now. An unlit shader doesn't need any information about the light, so it just calculates some color for the pixels that are going on an object. Image effect shaders are used to cover the entire screen generally, and sort of like working on a texture. And compute shaders are used when you're not necessarily trying to calculate something that is the color of a pixel. Maybe you're trying to simulate physics, and you could run that and do computation like that on your GPU. Just because your GPU is very powerful, you can do other work on it. So I'm going to choose unlit shader, and I'm going to call this goal shader because I think as I'm playing my game, the goal object really needs some love here. So let me stop the playback. So this goal shader, let's open that up and check it out. So when you first open a shader in Unity, it's going to, well, in Visual Studio, show you the code, and it looks like a structure. This that you see here, this structure is called ShaderLab. So that's the file format that Unity has chosen to describe the shader itself, the different data that the shader needs to do its job, and then include the code that actually performs the shading. So you can see that here. We first have a description of the shader name. Goal shader is filled in there already because that's what I named it. But it also has a category name here, and you can change this as much as you want. In Unity, when you create a material, let's create our material, goal material. You're going to get a choice in the inspector of what shader to use. Here's standard shader, that's a nice one. But I can go to unlit, and I'll find goal shader in there. So whatever you put before that slash, you'll make a new category. You can make your own categories of shaders. I'm going to select Gold Shader here just so that it's applied there. And you can see with an unlit shader, unlit shaders don't show much of anything. They're just flat coloring across, and you have to do all the calculation for what that color is going to end up being. Okay, so back in Visual Studio, we want to take a look at the rest of this Shader Lab syntax. So we've got our category, we've got the name of our shader, and properties is going to be a list of properties. Here we just have one. This is the texture information that's coming in, and you see that in Unity over in the inspector there's a texture selector here, so you can choose a texture. I don't know, maybe that's fine. And you can choose some of the options, tiling and offset for that. But this is what that property is providing in Unity. And it's also saying that it's a two-dimensional texture called main text, and the default value is a white texture. So just Unity has this default white texture that it'll use to fill it in if you don't provide a texture. This subshader section is going to contain passes and some other information about the shader. Here we have a tag that Unity recognizes, render type, that says it's going to be drawn opaque, so it's going to ignore transparent information. You can change this to transparent if you want it to actually like punch holes in your object where it's transparent. And then LOD, level of detail, is just a number for when the shader is going to be used as the camera is moving closer and farther. So we have passes in the subshader section, and each of these passes contains an actual shader program. So this section here, CG program all the way down to end CG, is the actual shader code that's going to run on your GPU. This is written in a language called CG. It's C for graphics, but they don't call it that much anymore. And it's created by NVIDIA and Microsoft together, kind of based on Microsoft's own HLSL shading language that they use for Direct 3D. If you were using that HLSL, or if you were using OpenGL and their shading language, which is GLSL, you would see a lot of the same stuff. They're all fairly similar. So in CG, you write this code, and this code will be converted to whatever shader binary program language, whatever, that the GPU needs to run this. So it starts off with a few pragmas to set up some information that CG is going to use to detect which functions you're going to be using. Here we have a vertex shader named vert, so this is the name of the function we're going to use, and a fragment shader called frag. So we'll look for the frag function to do fragment shading work. And so these are the two primary types of shaders. Vertex shaders, they change and modify the vertex data that's coming in. Say you provide a cube into this shader. It's going to look at each one of those vertices separately, and it can calculate new positions for them. So this is really commonly used to transform those vertices for camera projections, but it can also be used for making things wiggle and jiggle and wave and all sorts of things, distorting the shape. And the shape is only distorted visually. It doesn't actually change the geometry, it just changes the pixels and how they show up on the screen. The fragment shader, sometimes called a pixel shader, is what determines the specific color of a pixel. And so you are, in this fragment function, you are pretty much asked, here's a pixel, what color should it be? And you have to figure out what color it should be based on what effect you're going for and what textures and whatever else that you're considering. So there's some other Unity specific things here, and then a couple of structures that are going to provide the interface of data between these shaders. So you can see app data, and it has vertex information and UV information, texture coordinates. You can see a V2F structure. This is vertex to fragment, and it has UV information and it has vertex data as well. And when you look at the actual functions here, vert and frag, vert is our vertex shader, and it is taking as input this app data structure. So app data is what Unity is filling in and giving you in the vertex shader. In the vertex shader, it is creating this V2F object, filling in information from what Unity sent, this v.vertex, v.uv, and then it is returning that V2F. And that is vertex to fragment because that is the input to the fragment shader. So the vertex shader goes first, figures some things out for which vertices are going to be messed with and how they're going to change, and then passes information on to the fragment shader. So there are separate stages of shaders. And the fragment shader takes this in and figures out a color. So here this is a fixed 4, which you can think of as a 4-dimensional vector. Really it's just R, G, B, and A color components. And right here it is just getting them from a texture. So it's getting them from the main text object at these coordinates, the UV coordinates from this V2F structure. So once it gets those red, green, and blue and alpha transparency values, it stores them in this color variable, does some stuff, who cares about fog, and returns that as the result. So we can mess with this a little bit. Let's just change this and say I'm going to use, instead of fixed 4, I'm going to use float 4. They essentially amount to the same. They're both 4-dimensional vectors, RGBA, but they use a different representation for decimals, and so it's not really a big difference. You can usually ignore the difference. So let me change this to 1. Green will be 1, 0, and 1. All right. So this should be full red, full green, no blue, fully opaque. So what is red and green together in terms of additive light combinations? Let's see. It looks yellow. So now, if I apply my goal material to my goal, canvas is in the way. There we go. So if I apply my goal material now, because it has that shader set, it's going to turn it flat yellow. I'm playing around and just this super yellow thing pops out. Alright, cool. So that's a quick introduction to shaders, and we will get into a little bit more involved explanation of these things and changing how this goal looks so that it's actually cool.